Hello, today's topic is chemical formulas and nomenclature. And before we begin, I'd like to review a couple of the concepts that we talked about in Chapter 6, our unit on chemical bonding. I'll begin by asking the question, what does the chemical formula of an ionic compound tell you? Let's take an example. The ionic compound calcium fluoride has the formula CaF2. Now, does that tell us that calcium fluoride exists as molecules that are made up of one atom of calcium and two atoms of fluorine? No, you know that ionic compounds do not exist as molecules. Instead, the correct term for the structure of an ionic compound is a crystal lattice. And here's a picture that describes the crystal lattice of calcium fluoride. The formula CaF2 simply tells us that in the crystal lattice, the simplest ratio of calcium 2+ cations to fluorine minus anions is 1:2, or that there are 2 fluorine anions for every calcium cation. That collection we call one formula unit of calcium fluoride. Remember the term formula unit. How do we predict the formula of an ionic compound? How do we know that calcium fluoride has the formula CaF2? Well, we base that on the principle of electrical neutrality. We know from its position in the periodic table that calcium exists as 2+ cations. A calcium atom loses its 2 valence electrons to acquire the configuration of the previous noble gas. We also know that fluorine gains 1 electron to fill its valence shell, acquiring the configuration of neon. And using the principle of electrical neutrality, we see that we need 2 fluoride anions for every calcium cation, giving us a formula of CaF2. What about a molecular compound? In terms of molecular compounds, we call the formula the molecular formula. The molecular formula tells you something more specific. For example, in the molecule dinitrogen tetrafluoride, which has the formula N2F4, we do not express the formula as just the simplest ratio of one element to another. In fact, what that tells us is that one molecule of dinitrogen tetrafluoride contains exactly 2 nitrogen atoms and 4 fluorine atoms. And here is a depiction of that molecule. Check out that nice trigonal pyramidal geometry at each of the fluorines. Each of the nitrogens. So now let's move on to the main topic, which is nomenclature of binary compounds. You may not be familiar with the word nomenclature, but nomenclature simply means a systematic method of naming things. And in this case, we're going to learn a systematic method for naming both binary ionic and binary molecular compounds. What's a binary compound? Well, you recall a binary compound is a compound that is made up of exactly 2 elements. And there are a number of different types of binary compounds, but the ones that we're going to be most concerned with fall into one of 2 categories. We're going to deal with binary ionic compounds and binary molecular compounds. So let's look at how we name these compounds in each case. To name an ionic compound, there's a simple rule. The name of the ionic compound is simply the name of the ions. By convention, we name the cation first and then the anion. Similar to the way in the chemical formula, we have the cation first followed by the anion. The name of the cation is simply the name of the metal. So for example, the cation formed by sodium, Na+, is simply called sodium. It's pretty easy. The name of the anion is formed by taking the root of the element name and adding the suffix IDE, or ide. So let's look at some examples. CaBr2, I know that this exists as calcium 2+ cations plus Br- anions. The name of the cation is calcium. The name of the anion, I'll take the root of the name of the element bromine, which is brome, and add the IDE ending to give me calcium bromide. Li2O, I know that this consists of Li+ cations and O2- anions. So I will name the cation lithium. In this case, the anion, I'll take the root of the element oxygen and add the IDE ending, so this becomes lithium oxide. Why don't you pause the video and try the last one for yourself? Okay, if you did this correctly, you recognize that aluminum exists as cations with a 3+ charge. Selenium, based on its position in the periodic table, consists of anions with a 2- charge. The name of the cation is aluminum. and the name of the anion is selen, the root of the name of the element selenium, with the IDE ending, so aluminum selenide. Let's consider the ionic compound that has the formula FeCl2. If I break that apart into its ions, I see that the iron must have a 2+ charge. Now, iron is a transition metal. It occurs in the D block. You cannot tell based on its location in the periodic table what its charge will be. But I figured it out based on the fact that the anion, chlorine, has to have a single negative charge. Chlorine never forms a monatomic anion other than one with a single negative charge. Okay? So to name this compound, I would call it iron chloride. The problem is there is another compound that has the formula FeCl3. That clearly also contains chloride anions, but because there are 3 chloride anions per formula unit, I know that the iron has to have a 3+ charge. Well, I can't name both of these compounds iron chloride because that would be ambiguous. Every unique compound must have a unique chemical name. So the way that we solve this problem is as follows. If the metal is capable of forming more than one type of cation, meaning cations with different charges, after the name of the metal, put in Roman numerals in parentheses the charge on the ion. Okay. So if the metal can form more than one type of cation, state the charge on the cation in Roman numerals after the name of the cation. So the first compound, FeCl2, would be named iron 2 chloride. The second compound would be named iron 3 chloride. Well, which metals are these? All of the D block metals can form more than one type of cation, and 5 of the P block metals can also form more than one type of cation. They are indium, tin, thallium, lead, and bismuth. You don't need to memorize those will be given to you. How do you know the charge on the cation? Simple. You figure it out based on the charge on the anion. So for example, Cr2s3, don't know by looking at it what charge chromium will have because it's a D block metal and it can have a variety of charges. But in this particular compound, we know the sulfur has to exist as S2- anions using the principle of electrical neutrality, meaning that the sum of the charges have to add up to 0. We can figure out that the chromium must have a 3+ charge. So to name the compound, I would call this chromium 3 sulfide. Well, what we've just learned how to do is to take the formula of a binary ionic compound and from it deduce the name. The question is, can we go in the reverse direction? If I give you the name, can you write the formula? For example, lead 4 fluoride. Well, you notice in the previous examples, in going from the formula to the name, I took the trouble to write out the symbols of the ions that make it up. That helped me name it. Doing the same thing in this direction will also be very useful. So if you are given the name of a binary ionic compound, the best thing to do is simply write out the symbols of the ions that are contained in it. So for example, lead 4 fluoride. I know that the cation must be lead 4. Lead is Pb. The 4 in parentheses in Roman numerals tells me that the charge is 4+. Fluoride is unambiguous. Fluorine never does anything except form an anion with a single negative charge. So I combine these using the principle of electrical neutrality, and I come up with the formula PbF4. Rubidium arsenide, I can do the same thing. Rubidium is a group 1 metal, so it only ever forms a cation with a single positive charge. Arsenide, arsenic is a metalloid in group 15. It will gain 3 electrons to form the configuration of the next noble gas, As3-. Using the principle of electrical neutrality, I get the formula Rb3As. Why don't you pause the video and try the third one yourself? Okay, scandium-3. The symbol of the element scandium is Sc. I know the 3 in parentheses in Roman numerals refers to a 3+ cation. Selenide, selenium forms a 2- anion. So we combine these and we get the formula Sc2Se3. Add my negative charge there.